recording. And so, like I said, I'm going to kind of go a little fast today. Wrote everything out fairly carefully, and you know, it doesn't mean you can't stop me or text me or something in the chat. Yike. Okay, chapter 13, real-time imaging. That is what we do, is real-time imaging. What we do. So
I'm sorry for the interruption. For lab, so we're not attending lab Monday?
No, let me talk to Melissa and see whether or not we just do something asynchronous or if we have you guys come in. I would like to see you guys come in on, well, Friday and Monday. It's the same group. No, it's group 2 and then group 1. So you'll each miss one. I'd rather see you guys come in.
Here's another question. Do we have to have an instructor there, or can we go in to just, I guess, practice on each other?
Well, that's the thing. If Melissa's going to be there, she's very busy, so she probably won't be able to be in there the whole time with you. So you kind of will be on your own. But practice, we definitely need practice. You know, you guys are already kind of screwed over with this whole COVID thing. So you know, I hate to leave, but I really have to do this this weekend. So yeah, and I'd rather see you come in. Let me talk to Melissa and see what she plans on doing in my absence. So.
Okay, thank you.
Oh, sure. B mode. So this is, remember I said Edelman he separates B mode from real-time or live imaging. Real-time imaging is real-time B mode. So some authors do not make a distinction. He does. No big deal. So it's B mode live. It is brightness mode live. Okay. So then we talk about some resolution with live imaging that we haven't spoken about yet, or at least not officially. We've kind of mentioned temporal resolution. That ability to look at a screen and not get seasick, or to look at a screen and not get so frustrated by the screen, waiting for the screen to catch up to your movements. And that has to do with frame rate. We have the ability or the inability to see in separate frames, I think around 18 hertz. So if frames are coming at you at 18 hertz or 20 hertz, something around that area, we really don't notice that it's individual frames. And so of course movies, you know, are individual frames, but we don't see that in a movie. Most movies run at 24, 26, at least they used to. Now with modern video, everything's out the door. But the frame rate is determined by a couple of things. Well, the book says a couple of things and then it adds something. And so that's why I wrote it in different color. Speed of sound and tissue. If the speed of sound was really, really slow, we would have to wait really, really long. And our frame rate would be horrible. Now, fortunately, the speed of sound is lightning fast in the body. And so it doesn't take a whole lot of time for us to wait for all the echoes to come back for the next pulse and the next pulse and the next pulse. So our pulse repetition frequency, frame rate and pulse repetition frequency are going to be related. It tends to be very fast. And the depth of imaging. So if you're, once again, so that will slow you down. If you're going deep, if you're imaging very deep in the body, you have to wait that much longer for all the echoes to return, and then pulse, and then a pulse, and a pulse. You can imagine how that would slow down your screen because you're spending so much time waiting. And then there's another one but Edelman makes us wait another page. So I'll hold off too. I really don't know why he does that, but I'll hold off as well. So hopefully that makes sense. Speed of sound in tissue is a limiting factor. Not much of a limiting factor, it's lightning fast. Depth of image, that's a bigger factor that we'll have to look at. Okay. Damn it. Okay. Reciprocals. Remember, reciprocals are basically inverse relationships, but they're perfectly inverse. One value times the other value equals 1. And it doesn't matter what the values are because they're always perfectly inversed. So in this case, what we're going to call the T frame, the time to make one frame times the frame rate is equal to 1. Well, so let's see what that means. What does that mean? It's right here. Didn't need to do that. If it takes 1/20th of a second for an ultrasound machine to create an image, 1/20th of a second to create your image on the screen, then the ultrasound machine will make 20 images in a second, right? That seems to make perfect sense. If it takes 1/20th to make one image, 1/20th of a second to make one image, then in a full second, it makes 20 images. By the way, that's frame rate. And images per second, that's another way of saying hertz, right? So 20 hertz is fine. It's not awesome, but it's fine. It's fine for most of our imaging. If you're doing a fetal heart, though, which is beating at 150 beats per minute, 20 images a second will image the heart pretty well, but there's going to be some motion artifact. So you actually want to do better if you're doing a very fast moving structure like that. But for most part, 20 hertz, that's okay. Another example, if on a road trip, it takes me 1/5 of an hour on average to think of a cringeworthy dad joke, then my hertz, my jokes per hour in this case, actually it wouldn't be hertz, my jokes per hour would be 5 dad jokes in an hour, which is about right. Which my daughter, if she's listening to me, is we're going to go on I think about it. No, I can keep it up for 10 hours, 5 dad jokes an hour. That's 50 dad jokes on the way up. She's freaking out. Okay. And if anything is not making sense, slow me down. I'm okay with that. I'll just redo everything. No. So what does a sonographer have control of? Depth and the number of pulses. Number of pulses. We really haven't spoken about how we determine number of pulses. Well, we kind of have. We've mentioned that a couple of times. Here's the last determining factor. So as far as I'm concerned, when we're up here and we mentioned speed of sound, depth of image, I would have put number of pulses here as well. He didn't do it, so I'm not going to do it, but I will mention it here. Depth, so we have direct control of the depth. We also have, to a pretty great extent, we have direct control of the number of pulses. So I've drawn here the transducer with an imaging depth that is fairly shallow, and then maybe a second later we've changed our imaging depth to something a little more deep. The greater the depth setting, that deeper setting, we have more time waiting for all the echoes to return. Therefore, our frame rate is slowed down. That's pretty straightforward. So that's inversely related. Inversely related. More depth, less frame rate. Inversely related. If an image is created with 100 pulses, and each pulse takes, this is from your book, and each pulse takes 1/1000th of a second round trip. What's another way of saying round trip? Pulse repetition period. Remember that? It's the pulse and then all the time between the next pulse. Well, that's basically all the listening time, including and then the pulse as well. So each pulse takes 1/1000th of a second round trip, or the pulse repetition period, then the time needed for a single frame, T frame. So let's look at this again. I'll get a little closer. We mentioned earlier that T frame, the time it takes to make one frame, is equal to the number of pulses we didn't mention, I'm sorry, we mentioned the reciprocal relationship. So let's give you, this is the first time that we're giving you T frame. I'm sorry, I almost blew over that. The time to make one frame. The time to make one frame is the number of pulses that make up that frame. Well, that makes sense. And then the pulse repetition period. Well, that should make sense. If it's if I have 100 lines of information going across my screen, or in other words, 100 pulses of information, you have to wait for each one of those pulses to come back before the next one goes out. So pulse, wait, 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 pulse, wait, 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 pulse, wait, wait, wait. Multiply those two together, you get your T frame. So in this example, we had 100 pulses, and a pulse repetition period is 1/1000, 1/1000th. And by the way, guys, when it's this easy, we could just cross out zeros. Makes 1/10 of a second. 1/10 of a second to create one frame. Now we can go further, get the reciprocal of 1/10 of a second, and find out what the hertz is. So 10, if it takes 1/10 of a second to create the picture, you get 10 pictures in a second. If we change, and I think this is still from the book, if our depth now is now 1/2 the original, we're going to change our depth. T frame is now 100 over 0.5 over 100. It's 0.5, I'm sorry, 0.5 over 1,000. Multiply these two together, you get 0.5 over 10. All right. To kind of figure out a better way of saying that, we just multiply both top and bottom by 2. When you multiply half, or 0.5 by 2, you get 1. 10 by 2, you get 20. You get 1/20th. Yeah, so far it's easier. Oh, trust me, I'm going to hit you with, no. We'll see. 1/20th of a second. So we've halved our depth. We've doubled well, we've halved the number of time, the time it takes to make one picture, one frame. Therefore, we've doubled our hertz. So we went from 10 hertz, which is painful to look at, to 20 hertz, which is actually fine. All right, flying. We are flying, all right. Now, we said that we had control over the number of pulses. Well, we do. We actually have a lot of control over that. Let's look at the previous problem where the round trip time, the PRP, was 1/1000th of a second, which is pretty typical, I think. Yeah. Except now we're going to make an image using one pulse instead of 100 pulses. Because before we started out as 100 pulses, each one takes 1/1000th of a second. What's our T frame? Well, in that case, if you used one, if you put one into this equation up here, where before we had 100, like up here, if we had only one, then there wouldn't be zeros in there at all to cancel out. You would have a frame rate of one. Let's just write it again. So T frame now is equal to 1. And this, by the way, you can't make a picture out of one pulse. So this is an impossible situation, but I just used it as a, one pulse. And it takes 1/1000th of a time to create that pulse. Well, what's your frame rate? I'm sorry, your T frame is 1/1000th to make that frame. Therefore, your frame rate, well, would be 1000 hertz, which would be pretty amazing frame rate. But remember, one pulse is impossible. Or we can go the other direction and have 2000 pulses, which in and of itself is unlikely as well. I wouldn't say impossible, but rather unlikely. It's too many pulses. So if we had 2000 pulses, each with a pulse repetition period of 1/1000th, same thing. So we've changed this to 2000 times 1/1000th. Well, actually makes 2000 1/1000ths. 2/1, or 2 seconds to create a frame. That would be pretty bad. That would literally be waiting 1001, 1002, that long just to make one frame of your image. And then it would start again 1001, 1002. So a half hertz is what you would end out with. The reciprocal of 2 is 1/2. And so that's not so good. That would be almost static imaging. In fact, it probably would be closer to the original static imaging, 2 seconds to create a frame. Now, the static imaging originally didn't take that long because there was 2000 pulses. There were other reasons like vacuum tubes and stuff, and all the electronics we don't have today. Okay, hopefully that all makes sense. Now I have a little purple arrow here going all the way up to here. Man, I thought this was going to take a lot longer. I am flying. Stop me, guys. Text me, chat me. If you want anything repeated, you could do it anonymously if you like. Okay. continue. What am I continuing? I'm continuing. How do we determine the pulses? I guess imaging depth, number of pulses. Okay. So how many pulses? I'm sorry. How many pulses? Okay, well, how many focuses? Whoops. How many focuses? How many focal points do you have on there? Just one, which is the minimum? Or do you have 5, which is a lot? And I'm going to go over these again. Sector size. Did you sometimes when you take that sector or even the color box, same difference, and you make it thinner, you can reduce your number of pulses. And then lines per angle. Lines per angle, what they're saying there, when they say angle, they mean like if you had a degree, one, you know, each one of these radians is like 1 degree angle, is what they're really, that's what they're saying with lines per angle. Yowza. Okay, so I wrote these out a little bit more clearly. Actually, yes, I like that. And we've talked about multifocus. Over here, we just have one focus, our minimum number of focuses. And it's one pulse, one focus, one pulse. It's focused right here. And if you're using an array transducer, it's a pulse and then it moves over again, pulse, moves over, pulse, moves over, pulse. But each line of sight has one pulse. Now, you add a second focus, you have 2 pulses. It takes twice as long to gather the information in that one line of sight. So we've already calculated that it takes your frame rate and cuts it in half. And it doesn't always cut it exactly in half according to our computer, but there might be other little things going on. But theoretically, cut it in half, because now 2 pulses, so it's, before it was 1 pulse and then move on. Now it's 1, 2 pulses, then move on. So you've doubled the number of pulses for your image. You have a better resolution, because now you've essentially extended your focals. By using 2 focal points, you've extended your focal zone and you've increased the resolution, which is great, unless it's slowing you down so much that it hurts to look at the screen. So adding a focus adds time that you may or may not have. Let's see, on this one, I was trying to draw.
It also depends on where you're scanning too, right?
Oh yeah. So, well, it all ties together. If you're scanning deep, you don't want to use, you're already taking a lot of time in the system because you're scanning deep and you have to wait for those echoes. If you're scanning deep and you've created focal points, now you're waiting and you're hitting the same line of sight 3 or 4 times. Now it really is, it's very noticeable. But if you're doing a thyroid and you put in 3 or 4 focal points, you're okay, because because you're imaging so shallow that you're already at a hertz of like 80 hertz. Well, if you're at 80 hertz, you have plenty of room to work with. So you could have that 2 or 3 times before you start to notice. But yeah, so it makes a big difference on where you're scanning. So this one is vector size or sector size. Sector size. Do they use the word vector or sector? They use the word sector. Sector size. Let's write that down. Sector size. So let's start with the green one. If that's, and this is going to basically show on your screen as, let's just say it's that large. Let's say that's the standard. What when you turn on the machine, let's say that's how big the image is. But then below it, let's use a different color. Let's kind of get the original color there. Below it, you decided to make your field of view, your overall field of view, smaller. You might have done this for a couple of reasons. One, maybe you just had so much stuff on your image that you didn't want to image. You didn't want to be responsible for all that other stuff because you're only looking at something right there in the middle. A little party hat. Here, I'll use my little star in the middle. And that's all great because you didn't want to show all the other stuff out here. But really a good reason to do this, another reason to do this, is if you're scanning deep, you want more than one focal point. So you have a couple of things that are working against you. The depth, you have multiple focal points, because let's say you're really trying to get a beautiful image. So that slows you down. So what you can do is you decrease the overall size and you've decreased the number of pulses. Like for instance, this original one here, let's see, 1, 2, 3, 4, 5, 6, 7 pulses. That's not really realistic. It probably had more like 70. But this one, 1, 2, 3, 4 pulses. That one will have the faster frame rate, right? That makes sense. There's fewer pulses. Should have a faster frame rate. Fewer lines of sight are creating your picture. And that's really just a matter of changing the overall size of your image. People don't do this a lot. I don't do it a lot, but I do it sometimes, for sure. So those are 2 ways of changing the number of pulses, the number of focal points, the width of your image, and then here's another one: line density. So I have 2 transducers running here with the same size. So the field of view on these are not changed. But the first one has an unrealistic, but 6 lines of information, 6 pulses, assuming we have 1 focal point, right? So 6 pulses created that. But I could change my line density if I want. So now I've doubled the amount of pulses in this second image. I now have 12 lines, 12 pulses. Same difference, really. Assuming I have one focal point here. That makes it twice as long. Oh my God. Okay, we might be doing 2 chapters today, but all right, we'll see. This one, I went through this a lot faster than I had imagined that it would be. So let's just talk about, because an obvious question, SPI, this book, I don't even have to look. I know the question is, what values make the slowest frame rate? Okay, so actually, oh yeah, it's right there on a table 13.6 on page 209. But we don't even have to look at it. So slow. Let me zoom up on that. I can't write that. Damn it. Ugh. It looks like I was slow when I drew that. All right. Slow frame rate, or let's see, 4. So the first thing we talked about was what? Depth. Let's see. I'll call it max depth. That's going to slow us down. We have to wait all that time for those echoes to come back before the next pulse goes out. Slow us down. And that was pretty much it with depth, right? And then we said, well, number of pulses. So pulses, and then I'll do a subheading. So max focal points. That will slow us down. What do we talk about? Maximum sector. That's actually really the field of view. Our field of view. If it's at its highest, then obviously there's going to be more lines of sight, more beams, more pulses. What was the next one? Oh, density. So now you have 5 focal points, a maximum 100% sector range as far to the left and right as it can go. And then you say, I'm going to go to maximum density. So you're packing as many pulses in between that sector as possible. Is there anything else? Density, wide sector, multiple points, and deeper imaging. No. So that's everything you could do to make it slow. And of course, we could really quickly write down fast, but it's pretty obvious, right? Minimum depth. And then under pulses, one focal point. That's an ugly looking one. Let's see. Minimum sector size. and then minimum density. So fast frame rate is good, right? That's good. I'm gonna put a smiley face here and everything, and I'm gonna put a sad face over here. Just like everything else in ultrasound, it's a balance. You can't always have minimum depths. You know, if you're scanning a liver, we've thrown that out the door right away. So that's not even a balance. That's just practicality. You have to. It would be great if we could scan the liver with 5 focal points, but we can't. If you do, it's horrible to look at. It's very difficult to scan like that. So you're forced to go with 1 focal point, maybe 2 focal points in the liver. If you're scanning the entire liver, you can't use a minimum sector. You'd only be catching small little sections of that liver at a time, and that's not what the doctors want. And if you go with minimum density, that's all well and good, but minimum density is kind of the same as saying minimum quality of your image. And sometimes we don't care. If I'm doing a carotid artery, if I'm looking, well, I want to be careful how I say that. When I do vessels, I'm more interested in getting all the Doppler I can out of a vessel, getting the spectral right, getting all my measurements correct, and the overall quality of the image is a little bit less important. It's not unimportant, it's just not as important. So I don't mind doing a lot of things over here, you know, using 1 focal point, minimizing my sector size, minimizing my density. That's all fine with me. Oh, you know what? Let's add something, since I've spoken way too fast today anyway. Oh, that's good. We'll have 11 o'clock. All right. I'm going to add something that we haven't spoken about in this chapter, but it really is. It's the same difference. Add-on tech. A wide color box. That actually does it too. I don't know why he doesn't mention it in this chapter. He really should, because when you do what you're doing is you have to create your grayscale image. So let's say all of this is up here in the grayscale. You create your grayscale image, and then the machine switches into Doppler, creates a color box, a color region of interest, then switches back to gray, then switches back to Doppler, and it does it so fast that we hopefully won't even notice it happening. We just simply see color on top of our grayscale image. The reason I said wide is the same exact reason. Is your sector. The height of the box doesn't really matter, because that sound beam has to go from the top of the box all the way through it, regardless. But the width of that box. So if we have a color box, that is wide and unusually short, just because I'm running out of room, that means, let's use red for color. That means that course, the wrong color red. You got your grayscale image, and then you switch to color, and now you have this color box with 1, 2, 3, 4, 5, 6, 7, 8, 10, let's just say about 20 lines of sight, 20 pulses to create that color box. And here's the little trick about color is that it's more than 20 pulses. And if you do a narrow color box over here, but let's just make it about the same height. Now I've got that same height box, but only 1, 2, 3, 4, 5, 6 lines. Obviously, that's going to take less time, which helps, by the way. When you're scanning a carotid artery and you're having difficulty getting color, one of the things you could do is narrow that box, and then the machine has more, it's spending more time on a smaller region of interest rather than on a larger region of interest. And it's one of the things that we could do to help us get color. Same thing with pulse wave. You throw a pulse wave in there, although, whoops. Well, that's going to slow you down regardless, but it's actually one line of sight, regardless of whether you make this box small or large. It's still just one pulse going, well, one pulse line. I don't want to say one pulse, Doppler is different. One line of sight going through, and you're collecting information along the dotted line here. So that'll slow you down regardless. There's no thinning that box out. It's already thin. It's just that one little line of sight. M mode, technically speaking, M mode should slow us down a little bit, just a little bit though, because what M mode does is let's just say we had an area. This is our entire field of view. Our entire field of view, let's just say, takes 1, 2, 3, 4, 5, 6, 7, 8 lines of information. What M mode will do is 1, 2, 3, 4, 5, 6, 7, 8. And then 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. So that one extra line should slow us down, but it actually be pretty minimal because it's really one line out of hundreds. So, wow, way too fast. Let's see. More about temporal resolution. Okay, so basically on page 208 of your book, it's more about temporal resolution. It's pretty much saying that this is a balance, like I've already mentioned. You want a beautiful view of a thyroid. Hold your hand very steady. Tell the patient to stop snoring or whatever they're doing. Have them hold their breath or whatever. Hold your hand very steady. You have a shallow view, 4 or 5 focal points. Maybe even have your color box on, but you know, let's make that color box as narrow as possible. You do all those things and you'll get the best ultrasound picture you can get. But if you're looking at a baby's heart and you do all those things, what you're going to have is a baby with just a blur in the middle of its chest, that blur being the heart. And so we actually have a heart setting on these machines. It's great. It does everything it can to increase the frame rate. So you hit that heart setting in the OBGYN settings and the OB settings, the frame rate like rockets up to 80 hertz, 80 frames per second. And that's very good. Okay, I'm not going to do 14 today. I already started recording 15. That 15 is long, but this 13 was a lot shorter than I thought. Okay, well, you guys have any questions on this? Does that seems pretty straightforward? All right. Let me stop sharing for a second because I don't want to accidentally show people's grades. It's got to be careful with that. Okay. Oh, I got to stop recording. You guys were going to let me do that too, weren't you?
Yes.